This video is going to be on the acids and bases, and it's going to be on the ionic product of water, Kw. So the dissociation of water is weak. It only partially dissociates into its ions in solution. The equation for this is water plus water in an equilibrium reaction to form H3O+, which is a strong acid, and OH-, which is a strong base. This equation can be simplified, and this forms H2O dissociates into H plus OH-, and this is done by basically just cancelling 1 mole of water from both sides. From this we can see that water acts as a bronzed-Lowry acid and base, and this characteristic makes water amphoteric. And just so you can clearly see this, here water has gained a proton to form H3O+, and here water has lost a proton to form OH-. So, deriving Kw. As with all equilibrium reactions, we can derive a Kc expression for the dissociation of water. This becomes Kc equals H plus times OH-, all divided by H2O, because products over reactants, don't forget. Because water dissociation is so weak, though, we assume that the H2O's concentration remains unchanged, so we consider this basically as a new constant. What we then do is we times the constant H2O across our Kc expression, and then what we're left with is a new expression, and this is Kw equals H plus times OH- in square brackets. So we need to know a few things about Kw. Well, at 25 degrees Celsius its value is 1 times 10 to the minus 14, and the units are moles squared decimeter minus 6. In pure water, equal concentrations of both the ions are formed, so then this forms the expression Kw equals H plus squared, and you may need to just remember that in some exam questions. Pure water is neutral because there are equal concentrations of the H plus and OH-, and this therefore means that the pH does not have to be 7 for a solution to be neutral. It purely just needs the concentrations of the H plus ions and the OH- ions to be equal. So why do we even care and need to know about the Kw expression? Well, we use Kw to find the pH for strong bases, and I've basically just done an example below. So the question was, find the pH at 298 Kelvin, which is 25 degrees Celsius, of a 0.15 molar concentration solution of NaOH. If you're not used to this M, this basically just means moles per decimeter cubed. And then, so at 298 Kelvin, Kw equals 1 times 10 to the minus 14, moles squared decimeter minus 6, that's been cut off there. So the first thing we need to know is that it's a strong base, and that just like strong acids, the concentration of the base will be equal to the concentration of the OH- formed, unless you have a diprotic base. So what we can then derive from this is the concentration of OH- is equal to 0.15 moles per decimeter cubed. What we then do is we use our Kw formula to find the concentration of H+. So we rearrange the Kw equals H plus times by OH- to give us H plus, and then we just do 1 times 10 to the minus 14 divided by 0.15, and this will give us our hydrogen concentration, which is 6.67 times 10 to the minus 14. The final step is pretty easy now that we've got our hydrogen ion concentration, and we just use our pH equation. So subbing our concentration into the minus log base 10, we get an overall pH of 13.18, which sounds perfectly viable because it is a strong base and it's pretty close to 14, which is very basic. And that's all you really need to know for the ionic product of water, Kw.